practice of running separate wires to each lightning rod offers several advantages in terms of safety and reliability. While not always mandated by electrical codes, it's often considered a best practice, especially in areas with specific requirements from the local power company, sometimes referred to as the POCO. One key reason for separate runs is redundancy. If one grounding conductor is severed or damaged, the other conductor still provides a path to ground. This ensures that the lightning protection system remains functional, even in the event of a single point of failure. A break in a single conductor doesn't compromise the entire system's ability to dissipate lightning energy safely. Electrical codes provide guidelines for grounding and bonding to ensure electrical safety. The NEC, or National Electrical Code, outlines minimum requirements for grounding electrode systems. While it might not explicitly require separate runs to each rod, it emphasizes the importance of a low-impedance ground path. Separate conductors can contribute to achieving this low impedance by providing parallel paths for fault current. The local power company may have additional requirements beyond the NEC. These requirements can vary depending on the specific location, soil conditions, and the utility's own standards for grounding and bonding. It's essential to consult with the local power company and the authority having jurisdiction, sometimes called the AHJ, to ensure compliance with all applicable regulations. When installing lightning protection systems, it's important to consider the materials used for the grounding conductors. Copper is a common choice due to its excellent conductivity and resistance to corrosion. The size of the grounding conductor is also critical. The NEC specifies minimum conductor sizes based on the size of the service entrance conductors. The larger the service entrance conductors, the larger the grounding electrode conductor must be. The grounding electrode system typically consists of one or more grounding electrodes. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The NEC specifies the requirements for each type of grounding electrode, including the minimum length, size, and installation depth. When using ground rods, they must be at least 8 feet long and driven into the ground until at least 8 feet of contact with the soil is made. The rods must be made of approved materials, such as copper or galvanized steel. When using ground plates, they must have a surface area of at least 2 square feet and be buried below the permanent moisture level. Metallic water pipes can be used as grounding electrodes if they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet. The connection to the water pipe must be made within 5 feet of where the pipe enters the building. In addition to grounding electrodes, bonding is also an important aspect of electrical safety. Bonding involves connecting all metallic parts of a building together to create an electrically continuous path to ground. This helps to equalize the voltage potential between different metallic parts and reduce the risk of electric shock. The NEC requires bonding of various metallic components, including metal water pipes, metal gas pipes, metal conduits, and metal enclosures. The bonding conductors must be sized according to the size of the service entrance conductors. The NEC also specifies requirements for bonding equipment grounding conductors. Equipment grounding conductors are used to connect the non-current carrying metallic parts of electrical equipment to ground. This provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and de-energize the circuit. When installing grounding and bonding systems, it's important to follow the manufacturer's instructions and all applicable codes and standards. Proper grounding and bonding are essential for electrical safety and help to protect people and property from electrical hazards. A qualified electrician should perform all electrical work to ensure that it is done safely and correctly.